In the last lecture, we saw that when we take a product of two functions and differentiate it n times, then we get an expression which involves binomial coefficients. Now I am going to try to do the same thing with the chain rule. What happens when we differentiate a composition of functions n times? So, we want to compute something like dn dx to the n f of g of x. The answer is given by Faà di Bruno's formula. This formula dates back to about 1857. It is due to the Italian mathematician Francesco Faà di Bruno. I will use a certain notation. I'll use, we already are using this notation f prime x to denote d dx f of x, and we use f double prime x to denote d squared dx squared f of x, and so on. We could keep putting more and more primes, but that becomes a bit cumbersome when we want to talk about, say, the seventh derivative. So, what we do is we define f in brackets n of x to be dn dx to the n f of x. Now, before we go to the general statement of Faà di Bruno's formula, let us try some experiments ourselves. So, what happens if I take f circle g prime x? Well, this is the first case. This is just given by the chain rule, f prime of g x times g prime of x. Let us try the second derivative. So, f circle g double prime x. So, we need to differentiate this product, and so we will use Leibniz's product rule. So, first we must differentiate the first factor in this product. So, that we will just differentiate using the chain rule. What we get is f prime prime double prime g x times g prime x, and then we had that g prime x term, and then we must differentiate the second factor, keeping the first factor the same. So, f prime g x g double prime x. Let us try the third derivative. And now things get a bit more interesting. So, we have to differentiate the second derivative once more. So, let us start with the first term. So, this is f double prime x g x times g prime x. Let me write this as g prime x whole squared. Now, let us differentiate this. So, if we differentiate the first factor, we will get f third derivative g x times g prime x, and now we get the cube of g x because of the chain rule, another factor of g prime x comes out. And then we have f double prime of g x, and we must differentiate the second factor. So, if you differentiate this, what you get is 2 g prime x g double prime x. Here we have used the chain rule again. And now let us go to the second term in the sum. We differentiate again the first factor and then the second factor. So, if I differentiate the first factor, I get f prime f double prime g x times g prime x with the second factor g double prime x plus, and now we must differentiate the second factor. So, what we get is f prime g x g triple prime x. So, let me just collect the terms here, and you see that this situation is slightly more complicated, right? F double prime g x g prime x cubed plus, notice that the second term and the third term here are really the same. There is the second derivative of f, and then there is a g prime x and a g double prime. So, I can combine them and I can write it as 3 times f double prime g x times g prime x times g double prime x, and then the last term, which is just f prime g x g triple prime x. So, you see the situation is getting quite complicated very fast. Already at the third derivative we have 3 terms, and it is not clear what these coefficients 1, 3 and 1 are trying to tell us. Well, they could be binomial coefficients, but no, it turns out that no, those would be 1, 2, 1, right. So, this is 1, 3 and 1. So, what are they exactly? And it turns out once again that these have interpretations in terms of certain counting problems. Now, the counting problem that is involved here is the problem of counting set partitions. So, what is it? So, let me give you the definition. A partition of a set S is a collection of subsets of S such that each element of S occurs in exactly one subset of that collection. Okay, I will illustrate this by examples. So, the example that we will be mainly interested in is what I will call uppercase pi of n, which is the set of all partitions of the set box n. This is the set of integers from 1 to n. Let us look at this more specifically. What is pi of 1? So, this is the set of all partitions of the singleton set 1, and there is only one. You have to look at a collection of subsets of the set 1 such that each element, the only element here is 1, occurs in exactly one of them. So, this consists of only one subset, which is singleton. Let us look at what happens with partitions of 2. Now, there are two possibilities. Either you have 1 comma 2, a collection which has only one subset, namely the full set 1 comma 2, or you can look at the collection which consists of two subsets, namely the singleton set 1 and the singleton set 2. Let us look at one more case just to make it abundantly clear what we are talking about. What about pi 3? So, now you have several possibilities. Either you can take the full set 1, 2, 3, or you can break it up into 2 blocks. You can have one set of size 1, say 1 and then 2, 3, or you can have 2 and 1, 3, or you can have 3 and 1, 2. And finally, you can break it up into 3 subsets, all singleton. And we could try writing pi 4 and so on. This notation with curly brackets is getting very cumbersome. So, let us see if we can think of some simpler notation. So, there is a standard notation for these set partitions. Firstly, there is a name for the subsets. The subsets are called blocks. These are called blocks. And what we do is we write a set partition by just writing all the blocks, but we write each block in increasing order and we arrange the blocks in increasing order of their least elements. So, let me do it in this example of set partitions of 3. So, here we have the set partition 1, 2, 3, it is a single block. Then we have 1, 2, 3. So, this signifies that 1 is in a one block and 2, 3 is in another block. Let us look at this 2 comma 2 is one block and 1 3 is another block. I will write this as 1 3 2. See, whether you write the subset 1 3 first or the subset 2 first does not really matter, because we are just looking at this collection of subsets. We are not thinking of it as an ordered collection. So, it is customary to arrange the blocks in increasing order of their least elements. And finally, we have 1 2 3. Again, I have brought the block which contains 1 to the left. And finally, we have 1 2 3. Let me look at a bigger example. So, here is an example of a set partition with 3 blocks, and it is a partition of the set 1 to n. So, I have 2 5. So, this belongs to pi 7. This really denotes a set partition whose blocks are 1 comma 3, 4 6 7 and 2 5. So, we will say that the block sizes are 2, 3 and 2. So, how would we enumerate partitions of 4? So, we could start in the same way. We could first list all the set partitions which have, to start with we will just have the set partition 1, 2, 3, 4, and then we can go down and try to list set partitions with 2 blocks, set partitions with 3 blocks, and finally set partitions with 4 blocks. But there are quite a lot of set partitions in this case, and it is entirely possible when I was trying this at home, I missed out a couple of these set partitions. And then I had also accidentally written one set partition twice. So, we do not want these kinds of things to happen. What we need is a systematic way of writing down all the set partitions of 4. So, there is a method, there is a recursive technique and it is a way of if you write down all the set partitions of n minus 1, it is a way to get the set partitions of n. So, starting with the set partition of n minus 1, I will get a bunch of set partitions of n, and if I run this process over all the set partitions of n minus 1, I will end up getting all the set partitions of n. So, it is based on this basic idea. How do you get a set partition of n from the set partitions of n minus 1? So, you start by take a set partition of n minus 1, and now you want to construct a set partition of n. You have 2 choices, either add n as a singleton block. The other option is you add n to an existing block. Let me illustrate with an example. So, in our example we had a set partition of 7, namely 1 3 4 6 7 2 5. So, let us look at this 1 3 4 6 7 2 5. Now, what are the set partitions of the set 1 to 8 that I can get from this? So, I have 2 options. So, I need to take 8 and somehow include it in the set partition. I have 2 options, either I add 8 as a singleton block, and what will I get? I will get 1 3 4 6 7 2 5 8, or I have the other option of adding 8 to one of the existing blocks. So, 1 3 8 4 6 7 2 5. Here I have added 8 to the first block of the original set partition, but I could also add 8 to the second block. I get 1 3 4 6 7 8 2 5, or I could add 8 to the third block 1 3 4 6 7 2 5 8. So, you see from this set partition with 3 blocks, I got 4, this set partition of 7 with 3 blocks, I got 4 set partitions of 1 to 8. Some of them have, oh, here this 8 is supposed to be in a block of itself. So, I got 1 set partition with 4 blocks and I got 3 set partitions with 3 blocks. And in fact, given a set partition of 1 to 8, any of these partitions for example, I could just remove the 8 and see what is the set partition of 1 to 7 that I got. That will be this partition from which it was constructed. So, the point finally upshot is that every set partition occurs uniquely from this construction. Every set partition of, let us say, we usually denote set partitions by lowercase pi, not to be confused of course with the ratio of the circumference of a circle to its diameter. Little pi in pi n occurs uniquely in this way. Let us try to use this strategy to write down all the partitions of the set of numbers 1 to 4, starting with the set of partitions of the numbers 1 to 3. So, first let me write down the partitions of 1 to 3. So, I have firstly this single block consisting of all the numbers 1, 2 and 3. Then I have the guys with 2 blocks 1, 2, 3, 1, 2, 3 and 1, 3, 2. Not to confuse this bar with a 1. And then I have the only partition with 3 blocks. So, in this 1, 2, 3 case, I have 2 options. I always have the red option, which is to add 4 as a block by itself. And then I have the green option, which is to add 4 to an existing block. Here there is only one block. So, when I add 4 to an existing block, I just get 1, 2, 3, 4. Now, let us look at this 1, 2, 3. So, I have to add 4 as a block all by itself, or I add 4 to the existing block, in which case I have 2 choices. I have 1, 4, 2, 3, or I have 1, 2, 3, 4. Then the next case I have 1, 2 and 3. So, I want to add 4 to this. I can either add 1, 2, 3, 4, 4 as a separate block, and then I can add 4 to an existing block 1, 2, 4, 3 or 1, 2, 3, 4. And then I have again 1, 3, 2. So, I can add 4 as a separate block 1, 3, 2, 4, or I can add it to an existing block 1, 3, 4, 2 or 1, 3, 2, 4. And finally, I have this singleton block case. So, I add 4 as a single block, I get 4 blocks 1, 2, 3, 4, each block is singleton, or else I get 3 different options now. I add 4 to the first block, I add 4 to the second block, or I add 4 to the third block. And so, totally I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got 15 partitions of 4. And you can check for yourself that these are all indeed distinct set partitions, and I have listed all of them. So, now given a set partition, I have 2 things that I want to talk about notationally. So, if pi is a set partition, I will denote by absolute value of pi the number of blocks of pi. So, for example, in the set partition here 1, 2, 3, 4, what do I have? This is 3. The number of blocks of pi is 3. and given a block I can talk about its size. So I'll denote that by absolute value of B. So size of a block. So in this I have 3 blocks in this 1, 2, 3, 4. This block has size 1, size 2, this block has size 1, and this block again has size 1. Okay, so with this background, we are ready to state Faà di Bruno's formula. And this is not the usual version, so I'll call this version 1, and later I'll modify it a bit to give you the usual version that you'll find in most books. And the formula states the following. So if you were to try to compute f circle g, the nth derivative of x. So firstly, you would need to know that g is n times differentiable at x and f is n times differentiable at g of x. But if these were true, then what you would get is a sum, and surprisingly what happens here is it's a sum over all set partitions of n, and then you would take f, and how many times would you differentiate it? The number of blocks of pi. And then you would have a product over the blocks of pi, and then g differentiated the size of the blocks many times of x. That's the formula. So it looks like quite a handful. Let's try to understand it first using some examples. So let's just see what this says in the case of n equals 3. So then we have how many set partitions did we have? Remember, we have 5 set partitions. So we have pi is 1, 2, 3, or we have 1, 2, 3, we have 1, 3, 2, and we have 1, 2, 3. And then finally we have the set partition where all the blocks are singleton, which is just 1, 2, 3. And let's write down the terms corresponding to each of these. So if I take pi to be 1, 2, 3, how many blocks does this have? Well, this just has one block. So I should take the first derivative of gx. And then I must take the product over the blocks. It has only one block and its size is 3. So I must take g triple prime x. Okay. Now let's write down the factor corresponding to the set partition 1 in one block and 2, 3 in another block. So now how many blocks do I have? I have 2 blocks. So I have f double prime of g of x. And then I have one block of size 1, so I write g prime x. Another block of size 2, I write g double prime x. And the same is here. I have 2 blocks, one of size 2 and one of size 1. So again I get f prime gx, g prime x, g double prime x. And I have this once more here, f double prime gx, g prime x, g double prime x. And finally I have this partition with singleton blocks. So if you think about it, there are 3 factors. The set size is 3 f triple prime gx times g prime x whole cubed. And if you think about it, this is f prime gx g triple prime x plus 3 times f double prime gx times g prime x times g double prime x plus f triple prime gx plus g prime x the whole cubed. And this is exactly what we had worked out earlier when we did the example.